Have you ever just thrown a ball straight up in the air, watched it go up, kind of hang there for a second, and then come right back down? Seems so simple, doesn't it? But the physics behind that little trip, it's this amazing story of forces battling it out. And that's exactly what we're going to dive into today, the physics of falling. So let's kick things off with a classic thought experiment. We all get gravity, right? It's always pulling things down. So picture a skydiver jumping out of a plane. Why don't they just accelerate forever? I mean, why don't they keep getting faster and faster and faster until they hit the ground? What's going on there? What's stopping them? Well, the answer is this powerful, totally invisible force that's fighting back against gravity the entire time. You can't see it, but I can guarantee you've felt it. You know when you stick your hand out the window of a moving car? That push? Yep, that's it. It's air resistance. Okay, so let's properly introduce the main character of our story, this unseen but super important resisting force. Basically, anytime something, doesn't matter if it's you, a car, or a baseball, moves through a medium like air, that medium pushes back. It just does. And this push, this resistive force, has one job and one job only: to oppose whatever motion is happening. So if you're going up, it pushes you down. And if you're going down, it pushes you up. It's kind of like the universe's built-in speed bump, always telling you, hey, not so fast. All right, let's actually see this thing in action. We're going to follow an object's complete journey, starting right at the beginning, the moment it's launched upwards, fighting that tough upward battle. So, picture this. We've just launched this thing straight up. It's shooting upwards, full of energy. But from the very second it starts moving, there are two powerful forces already working together, conspiring to bring it back down. And you can see those two forces right here in this diagram. Check out the arrows. You've got gravity, that's mg, and of course it's pulling straight down. But look, because the object is moving up, that resistance force, R, is also pulling down. They're on the same team here, ganging up to slow this thing down. And you know what? The math totally backs this up. The total force, F, equals negative mg, that's gravity pulling down, plus a negative mkv, which is just our fancy way of writing the resistance. And that little v in there, that just means the faster you go, the stronger the resistance. So since they're both negative, it means they're both pulling in the same downward direction. It's no wonder stuff slows down so fast when you throw it up. It's literally fighting a battle on two fronts. Okay, so our object has run out of steam. It's hit its highest point. The upward battle is over. Now it starts that fall back to Earth. And this is where things get really interesting because the whole dynamic between these forces is about to flip on its head. Take a close look at this new diagram. Gravity, mg, well, it's still doing its thing, pulling straight down. But look what happened to R, the resistance force. It completely flipped. Because the object is now falling down, the resistance is pushing up. They're not teammates anymore. Now they're opponents locked in this epic, cosmic tug of war. So this is the key takeaway, right? On the way up, gravity and resistance are buddies, working together to slow things down. But on the way down, they're enemies, pulling in opposite directions. And that one simple change in their relationship makes the downward journey a completely different story. And putting them side by side like this just makes it crystal clear. The gravity arrow, mg, never changes. It's always pointing down. The only thing that's different is which way that resistance arrow, r, is pointing. Such a simple little change, but wow, does it have some huge consequences. So this tug of war on the way down, it's building to something. It leads to this amazing climax, this moment of perfect, beautiful balance. And this is how we get to something called terminal velocity. Now, here's the thing you got to remember about air resistance. The faster you go, the harder it pushes back. It's a simple rule. So as our object falls and gravity makes it go faster and faster, that upward push from the air just keeps getting stronger and stronger. It's fighting back with everything it's got. So what happens? What happens at that exact moment when the upward push from the air perfectly cancels out the downward pull of gravity? What happens when the tug of war is a perfect tie? You get terminal velocity. That's what happens. The forces are perfectly balanced, the net force is zero, and if there's no net force, there's no acceleration. The object literally can't go any faster. It just keeps falling at that one constant maximum speed. And this is such a cool, elegant little insight. Instead of doing all this complicated math with calculus and whatnot, there's a super simple shortcut to find terminal velocity. You just have to find the speed where the acceleration hits 0. That's it. Okay, let's try a quick example together. Let's say we have an equation for our object's acceleration. A equals 9.8 minus 0.4 v. Now, to find terminal velocity, all we do is use that shortcut. We just set A to 0. And boom, we're left with a super simple algebra problem. 0 equals 9.8 minus 0.4 v. Now, all we gotta do is solve for v. And when you run the numbers, you get 24.5 meters per second. Done. That's it. That is the absolute top speed this object is ever gonna reach while falling. How cool is that? No crazy math required. Okay, so this has been a fun little physics trip. But why does any of this actually matter? Why do we care about this tug of war between gravity and air? Well, as it turns out, this idea of reaching a balance, it's pretty much everywhere. I mean, this principle is absolutely critical for so many things. Engineers use it to design safer parachutes, right? They're literally designing for high air resistance to slow you down. Car designers are doing the exact opposite. They want sleek, aerodynamic cars to cut through the air with less resistance. It's even the reason raindrops don't knock us out. They all reach their own terminal velocity long before they get to us. So we've seen how this one invisible force, air, creates this perfect balance with the constant pull of gravity, and it completely defines how things fall. Kind of makes you wonder, doesn't it? What other invisible forces are out there right now, locked in a similar dance, shaping our world in ways we haven't even thought to look for yet?